description. Okay. So from here, based on our final derivation of momentum equation, alright, finally we managed to convert it into summation of force is equal to mass flow rate multiplied with V2 minus V1. This is the final form of momentum equation in the fluid mechanics. Based on this form, we can convert this form into three components, which is X component, Y component, and Z component. So when it is involved of Z component, we just put here, sorry, if we involve of X component, we just add additional X here. When it is involved of Y, just replace X with Y and Y. So from here, this momentum equation apply to stationary deflector. Alright, will apply to stationary deflector. So what is deflector? This is deflector that deflect the fluid from entering to the exit of the deflector. So this deflect the fluid. So this deflector is held by reaction force. That's why we call as stationary deflector, because of we have the reaction force Ry and Rx. So from Bernoulli equation, we know that V2 equal to V1. Alright, V2 is velocity outlet, same with velocity inlet. Because why? Because we apply Bernoulli equation. Remember our Bernoulli equation, which is V squared over 2G plus P1 plus Z. This over gamma. So this is actually the Bernoulli equation. By using the Bernoulli equation, this is 1, this is 1, this is 1, this is 2, this is pressure 2. Alright. By using this Bernoulli equation, you can see in this part, this Bernoulli equation in 2 points, velocity 1 is equal to velocity 2. Why? Because pressure is exposed to the external atmosphere. So pressure 1 is atmospheric pressure as well as pressure 2. So pressure 1 we can cancel out because the same. And Z1 and Z2 is we consider as a very small change in elevation. So we can cancel out. That's why leave only V2 and V1. That's why V1 equal to V2. Alright, I hope you understand, yeah? And here mentioned again, the pressure is constant. That's it. So based on our Bernoulli equation and the momentum equation, we derive the momentum equation applied to stationary deflector. It's very easy. I show you one example. Alright, this is summation of force in X component. This one we refer here, right? Equal to mass flow rate multiplied with velocity 2x minus velocity 1x. So summation of force, where is the summation of force in X component? You can see here we have Rx component only. So Rx pointing to the left. It's supposed negative Rx equal to mass flow rate multiplied with velocity 2x. So this velocity 2 is the final velocity reflecting to the X component. So in order to get the X component, V2 cos alpha. So V2 cos alpha minus V1. V1 is actually same with V1x, the same with V1. So V1 So now you can see this equation same with this equation. However, as we mentioned previously, B2 is same with B1. So can we replace B2 with B1? Yes, we can replace this B2 with B1. So B1 the same term, then we can factorize out. So that's why we get M B1 multiply with cos alpha minus 1. So far, you guys understand on how the equation coming from? Please comment there if you understand. Okay, thank you. All right, next we go to the moving deflector. So this moving deflector means this, you can see the deflector here is moving from the left to the right. You can see in terms of VB. VB is the motions of deflector. Alright, this the angle of deflector alpha. So here, once there is the motions, if there is a motions of this moving deflector, yeah, if there is a motion from left to right in terms of VB, alright, there is the change of momentum. Alright, the momentum means the change of momentum means the change in velocity. So, for example, the velocity here constant, the same velocity. Once it reach this portion, when it enter this deflector, enter the moving deflector, the velocity will change because of moving of this deflector. So let's say this B, all right, from here to here, the velocity doesn't change, constant velocity. For example, velocity here is 5 meter per second. And when entering this moving deflector, the velocity will change. It will be, for example, it will be 3 meter per second. So there are changes of velocity. That's why we need to apply the relative velocity to encounter the momentum change when entering this deflector. Okay. So, let's say, as I mentioned before, when the fluid enter this moving deflector, it will change the speed or velocity. So, it will change in this part. Okay, it will change. Alright, let's say we name as a VR1. This is velocity relative 1. And there is the moving of this deflector, which is we call as a VB. The summation of VR1 with VB will reflect to V1, which is the velocity from here, from the inlet of liquid jet until to the final of inlet velocity. This is V1. So VR1, right? The summation of VR1 plus VB is equal to V1. This V1 is the inlet velocity. Remember, yeah, the inlet velocity VR1 plus VB is the velocity of deflector motion will equal to V1. The V1 is absolute, yeah, absolute velocity. So V1 is actually absolute velocity. So when the question asks find the absolute velocity v1, so this is v1. So in order to get v1 is equal to vr1 plus vb, right? And we go to the point number 2. This is point number 1 and this is point number 2. Number 2, we look at here, right? This is point 2. Okay. So once the velocity reaching at the outlet here, this is we call as VR, still VR, relative to this frame. This is relative to this deflector, yeah? V relative to this reflector, V2. Alright, so we need to form the polygon, the triangle here, in order to know the summation of force. So V2, VR2 in this way. Okay, this is, let's take a look. This is VR2 and VB in the horizontal direction. Sorry, this is VB. And the summation of force is actually from here to here. This is V2. You can see here, this is a vector form. Alright, the resultant force. Here is a V2 is a resultant force. Same goes here. V1 is a resultant force. So the resultant velocity. The resultant velocity 2 is actually equal to VR2. Sorry, V2 is equal to VR2 plus VB. You can see, in order to get V1 here. Okay, you guys understand so far on how we get the V1 and V2 from the moving of deflector. Do you have any questions so far? All right. Okay. So this is how it looks when you involve derivations of moving deflector. All right. When there is a moving deflector, remember we have relative velocity to the deflector. So VR1 velocity relative to this deflector at point 1. All right. So again, in order to apply the momentum equation, we use this one. Summation. It is quite big. Alright, summation of force equal to M mass flow rate multiplied with V2 minus V1. When involved of the X component, we shall expand here. So summation of force in X component equal to mass flow rate V2X minus V1X. And again, summation of force in Y component is mass flow rate multiplied with V2Y minus V1Y. So here, in order to get the summation of force in the X component, let's take a look here. First, we apply this momentum equation. Okay. First, we apply the momentum equation in the X component. And then we need to know what are the forces related to the X component. So Here we have the Rx, the reaction force. This reaction force still holding this deflector, but it is moving this deflector. So here we can actually divide into two components. So this is R, Y, and this is Rx. Okay, because this is slanting. When there is a slanting, we can, sorry, this is Ry. Right, this is Ry. Right, because this is slanting, definitely we have the X and Y component. Right, so what are forces related to X component? Only these forces. So that's why summation of force, which is Rx, going to the left. So when the force to the left, we have minus force, negative Rx. Do we have any other forces? No. So we don't have any tangible force. We don't have any forces here. So from here, equal to mass flow rate, right? Multiply with V2x. V2, where's the V2? This is V2, you can see here, V2. V2x is actually velocity just exit the outlet of deflector. So definitely V2 refer to VR2. V2x refer to VR2, not V here. This is wrong, right? V2x refer to the velocity of the deflector outlet. This is total velocity. So we refer to VR2. So replace here VR2. This is in X component. So we must cos it with alpha. VR2 cos alpha and then minus V1x. So V1x is referred to VR1. Okay. So from here, you need to replace VR2 with this form that we derived previously. Okay, so that's why VR2 right. So what is VR2? What is VR2? In order to get VR2, what we need to do? V2 plus VB or V2 minus VB? Anyone please comment there? In order to get VR2, what to do? In terms of vector, V2 plus VB? Yes, correct Hakim. Yes. So VR2 is equal to V2 minus VB because VB going to the right. So we need to counter it with negative. You can see here negative. And how about VR1? How to get VR1? VR1 definitely V1 minus, yes, here, V. So with this equation in mind, we can replace this term, these two terms. All right, negative Rx equal to mass flow rate. VR2 replaced with V2 minus VB. Okay. cos alpha, this is the full bracket, minus VR1, which is V1 minus VB. Okay, so now we have V2 and V1, we have VB and VB. Remember that by using the Bernoulli equation, V1 equal to V2. Okay, so we can replace V2 with V1. V1 minus VB cos alpha minus V1 minus VB. So we look at here, we have the same terms, V1 minus VB, V1 minus VB. So we can factorize this velocity, all right? So finally, it will be like negative Rx equal to mass flow rate V1 minus VB. Okay, I continue here. Cos alpha minus 1. So far, do you guys manage to understand how the summation of force lead to this equation, everyone? Okay. Alright, if you don't understand, alright. Those, what's your question?
Doktor, kalau tengok dalam slide doktor ni, dia tulis VR1 equal to V1 minus VB. Lepas tu VR2 also equal to V1 minus VB. So it means VR1 equal to VR2
Which one?
at the before this. Ni apa tu? No. Tadi. Ni dekat bukan doktor yang di moving deflector tadi. Ni dia cakap VR1 equal to V1 minus VB. Lepas tu VR2 also equal to V1 minus VB.
Okay.
So it means VR1 equal to VR2.
Sekejap, yang mana satu saya tak nampak.
Yang ni, yang atas deflector.
Yang ni ke?
Bukan kan, sebelahnya. Sebelah kanannya.
Sini.
Sebelah yang ni, VR2, sebelah apa ni? Sebelah polygon tu. Ada equation VR2.
Okay, yang saya tulis, saya conteng ke?
Yang sebelah kan tu. Yang ada V2X equal to VR2 tu. Yang anak panah masuk dalam.
Betul.
Dia tulis VR2 equal to V1 minus VB.
V1. Okay, yang ni yang awak tak faham.
Saya tak faham tu. So maksudnya VR1 equal to VR2.
Okay, bukan macam ni. Okay, saya faham maksud awak tu. Okay, remember based on our Bernoulli equation, V1 equal to V2 that we previously discovered because of same external pressure.
Yes, doktor.
Okay. V1 sama dengan V1 equal to V2. Do you understand why V1 equal to V2?
Because there is no pressure at contour surface.
Okay, so because of Bernoulli equation previously, the same external pressure P1 and P2 and negligible of elevation, we come up with P1 minus equal to V2. So benda ni actually, this thing is actually the same like what I try to derive here. Okay. Okay, how to get VR2?
From the resultant.
Okay, from the resultant, correct. So VR2 equal to V2 minus VB. If we change the V2 with V1,
Oh, oh okay,
V,
I see.
V1 minus VB. Is it the same with this one?
Yes,
Those?
yes, doctor. Yes, yes.
Okay. Okay. So far, do you understand how it come from?
Okay, okay. I
Because
understand.
we have the same here. Okay. Anyone? That's a good question. Anyone wanna ask? Okay. So from this one, remember we have Bernoulli equation. V1 equal to V2. This actually they try to short form. They try to shortcut. Okay. This part they try to shortcut. Basically, it is VR2 equal to V2 minus VB. And because of V2 equal to V1, so they replace here directly V1. So that's why you can directly go here, understand here. Okay? So from here, we managed to get the summation of force in X component equal to negative Rx equal to mass flow rate dot V1 minus VB multiply with cos alpha minus 1. Okay? You can see it is the same. So when you apply again with V for the summation of Y, it is the same thing happen. Okay? Okay. So what to do to get the summation of this one? This one we have solved this one. So Fy, what is the force in the Y component? Definitely Ry. Ry is pointing upwards. So it is positive. Yes, it is positive Ry. There are no other forces. So equal M flow rate V2Y. So this is V2Y, Y component. So definitely VR2. Alright. So VR2 in Y component definitely sign. We sign it with alpha. Alright, because we have the, so this is a VR2. So we sign it with alpha, we get the VR2 in Y component minus V1Y. So what is the value of V1Y here? Anyone please comment? What is V1Y? Eugene, they, yes, correct. There is no vertical component. So just put it here 0. Alright. So that's why VR2, we replace VR2 with V2 minus V1 or V2 minus VB or V1 minus VB. That is why it turns out to be this equation. So you can see previously we got plus Ry equal to M flow rate. This is V, remember this is V R 2 sine alpha minus 0. So VR2 is actually V2 minus VB. So we replace this one, Ry equal to mass flow rate V2 minus VB, okay, sine alpha. So you look at here, it is almost the same. However, V2 is equal to V1. So that's why they replace V2 with V1. You can see the same equation. Alright, I hope you understand here how to get the momentum equation in X and Y component. Okay, one more thing that I would like to highlight here is that when the momentum equation apply to moving deflector, we are not going to use any kinds of mass flow rate. We need to use the specific flow rate. So the mass flow rate here we refer to, previously we discovered that summation of force equals to mass flow rate V2 minus V1, right? So mass flow rate here, we're going to use the different mass flow rate. So we are using the mass flux exiting the fixed jet with the change momentum. Because we have the change velocity, definitely we have the change momentum. So what is MR? So here we refer to M relative, yeah, mass flow rate relative. So here we refer to this mass flow rate entering. We refer to the mass flow rate entering this inlet. So M mass flow rate R, right? This mass flow rate, this is actually mass flow rate M. So we refer to M mass flow rate of R, relative mass flow rate. Alright. In order to get the relative mass flow rate, we refer to this equation. So M equal to rho A V R1. So velocity R1 we can replace with V1 minus VB. That is why you can see here the one that I have derived. So far, you guys understand? Okay, thank you. Remember, when the question involves moving deflector, use relative mass flow rate. If stationary deflector, use standardized flow rate. Right? So previously, I explained to you about the single moving deflector. In real case, it quite complex because we have a series of moving deflector. That is why we call as a cascade of veins. This we call is veins, the cascade of vein. So we have a staggered of vein, many veins here. All right. Why there are many veins? There are many of these veins because they need to maximize the power output. If there is only one vein, there will loss of energy. That's why they need to recover as much as energy. They introduce the cascade of vein. All right. So this cascade of vein will capture one energy. Once the moving, it hit this vein, it will capture another energy. That's why they try to rotate and reserve. They try to recover as much of energy from the turbine, for example. So we need to know a little bit about how it works, right? This, just try to imagine that this vein is moving, all right? Moving from the left to the right with velocity VB. Okay. Okay, I try to capture this and then I explain to you. Okay. Okay, so I want you to focus, yeah? And this part is quite complex. But once you focus on my lecture, it will be easier for you to do a revision later on. So, let's take a look. This is, we draw the cascade of veins. Okay, and then we have the water jet. We have the water jet. For example, this is the water jet. We have the water jet. This is water. Okay, so this water we name as V1. When the water entering this jet, is there any change of velocity? Please comment. Is there any change in velocity? Afiq Rohaizam, comment yes. What changes? Please comment. What changes? In terms of magnitude or direction or both? When the velocity entering this inlet, is there any change in magnitude, direction or both? It will change both, all right? It will change the magnitude and the direction. So the direction will be different, follow to this shape. So this one we call as VR1, all right? Velocity relative to this vein, 1. And then this vein is moving to the right, VB, all right? And from this point, number 1, we form the polygon. So how to form the polygon? So V1, we draw here, V1. And then this is VR1. This way or this way? Definitely this way. This is VR1 and VB. This is VB. Okay, so far you guys understand, yeah, how to form this polygon. All right. So next is, this is the inlet section. We call as a point 1. Yes, those VB always horizontal. Okay. Okay. Because we have a very, we call a very big cylinder, it's difficult to measure it in terms of circle. So we consider as the, okay, I understand what you mean. Okay, that is a good question. Why BB is always horizontal? Okay, like this. Okay, let me draw. Okay, this is a rotating shaft. And we have been here. Okay, so why this considered as a VB? Why VB always horizontal? Okay, because let's we try to zoom. Once the cascade is, this rotor is actually very big, all right? So we consider only this portion. So that's why you can see this is VB. Okay. Yes, we are taking tangential direction to the circle as the VB. Okay. Remember that we focus on control volume. All right. Control volume is only this portion. So that's why it looks horizontal. All right. For example, yeah. So this VB, remember that this, even though it is rotating, but we focus on control volume. So this is moving, only this portion moving to the right. Okay. So far, you guys understand how VB is horizontal based on our control volume. Remember, we use the Reynolds transport theorem. We only focus on control volume. Okay. So this one is actually the water jet. Okay. Okay. So now you guys manage to look to see how the real phenomena. We have the rotor, we have the vein. Okay. So this one, this is VB. VB always tangential to the circle. Okay. Do you have any more question? Okay. Alright. So from here, okay. So from here, let's go to the outlets, or we call as point number 2. So how the outlet form? Right. Once the velocity entering this region, okay, it will go outlet here. V R2. Okay. So because of VR2, we need to draw this one. So VR2 in this direction. Okay. So this is velocity relative at point number 2, and we have VB. So what is the resultant force? Sorry, what is the resultant velocity? Which direction? Resultant velocity. Resultant velocity we call as a V2. Alright, it is actually at the middle or some other location. So it is actually at the middle. So how to get? We form like this. Okay, this is parallel, and this is parallel to x component. So it meeting this point. So the resultant velocity. So this is we call as V2. So far, you guys understand? Okay, if you understand, please comment there you understand. Or if you have any question, feel free to raise up your hand. Okay. So from here, we need to define the angle. The angle is very important in this lecture. All right. So let's use different marker. Okay, use pink. Okay, so let's say this is continuously. Okay, and this point, the inlets of a deflector we call as a alpha 1. The exit of the deflector, okay, we call as alpha 2. Okay, and then the inlet of the jet V2, okay, okay, this one we call as the inlet of the jet is beta 1, right? This is referred to V2. How about V1? So V1 is actually in this direction, which is in between this. So, okay, sorry, it's not nice. So this direction. So this is the resultant of velocity 2. This is V2. You see here. V2, and then the angle here refer to this angle. This is beta 2. Alright, I hope you understand, yeah, what's the angle looks like. Angle of the water jet is beta 1, which refer to V1. Angle of V2 refer to beta 2. Angle of the deflector inlet alpha 1, exit is alpha 2. Okay, so if the mass, so now we apply the, alright, I hope you can see now it is the same. So in order to get the V, you see here, in order to get the VR1, alright, in order to get the VR1, it is actually VR1 equal to V1 minus VB. Okay. And then in order to get VR2, so here you can say that, alright, this is in order to get the V2, it is summation of VR2 plus VB. Okay. So this one. Alright. Now let's apply the momentum equation in X component. Alright. So apply momentum in X component. So summation of force in X component equal to mass flow rate V2X minus V1X. Okay. So the summation of force in X component. So we have to look at. Okay. We have the reaction force. So we have the reaction force basically holding this deflector. We call as the Ry and Rx. We have the reaction force holding this deflector, alright, in the X and Y direction you can see here. So what are the forces related to the X component? we have Rx. Remember, we have Rx. Rx going to the left. So it is minus Rx equal to mass flow rate V, okay, V2 x minus V1x. Okay. Okay. I think so. Basically, it is the same. If you want to apply the momentum in y component, just follow this force, this formula. Alright, summation of force in y component is equal to mass flow rate V2y minus V1y. So VFy refer to Ry, which is pointing downward. So it is negative. Negative Ry equal to mass flow rate. This is the same here. I will explain later on. Okay. So that's why you can see how the derivations looks like. All right, in order to get this deflector. So how the engineers, the company utilize the power outputs. All right, how they get the energy from the working fluids. So they apply this energy equation. All right, if all the mass exiting the jet has the change momentum, means the change of velocity. This negative Rx, this is actually the momentum in x component that we have derived previously. You can see here, this one. Yeah, negative Rx equal to mass flow rate multiplied with V2x minus V1x. You can see the same here. Only the x component of force is related to the power output because of the vein moving only x direction, not y direction. There are no motion of the vein here moving in the vertical direction. It always moves in the horizontal or tangential directions. All right. So that's why they consider the output power W dot equal to FV. Okay. So remember our okay, work done is equal to force time displacement. Remember, sorry, this work. Work done is referred to force time displacement. In order to get the power, we have to divide all this with time. So this divide with time, we get W dot equal to force multiply with which this is the displacement divide with time, which is velocity. That's why you can see here, this F refer to reaction force in X component. So we can replace this force with R component, with reaction force in X component, multiply with V, velocity of deflector, velocity of moving deflector, which is VB. And here refer to number of vein. If there are many vein, we have to multiply with that number of vein. So N. So in order to get the power output, which is W dot equal to number of veins multiplied with reaction force Rx multiplied with velocity of the vein, the moving vein, VB. So here is the equation to get the power output. Okay. So basically this is how the theoretical derivation works. So in the tutorial, all right, I will explain more on this question. Right, we have this part, the stationary deflector, we have the moving deflector, and we have the cascade of veins deflector. Okay. Okay, now we try to finish on we have finished on the theoretical part for the deflector. We learned about the stationary deflector. We learned about the moving deflector and cascade deflector. And next lecture, we're going to discover the momentum equation applied to the propeller. All right. So I give you 10 minutes to rest before we continue our lecture. We continue at 10:10 a.m. Okay, everyone. Assalamualaikum. Can you hear my voice?
Waalaikumsalam. Yes, sir.
Okay. After this, I'm gonna give you one task. Okay. After this, I'm gonna give you one task where in the e-learning, I will create a forum. All right. So after this, I'm going to upload this recording. The task is simple, right? I will upload this recording, and then you try to understand the lecture. And if you don't understand the lecture, please uh, please write your inquiry or your question that you want to ask in the forum. So I give every one of you at least one question. You try to post in the forum, all right? And then your friend have to answer your question, okay? Have to answer back your question, right? So how many questions that your friend gonna answer? All right, your friend gonna answer three different questions. Okay, for example, after this I will create one forum. All right, and then please, every one of you, this is the task. Every one of you, please read this lecture note on the momentum equations regarding the deflector and propeller, and post at least one question for every one of you, and you yourself have to answer your friend request, your friend question, three questions. So for example, friend A and friend for example, Ali and Abu. All right, Ali post one question, Abu have to answer three questions. Okay, so that means every one of you, the first task, every one of you have to post your question in the forum, and every one of you have to answer your friend question, not your own question. Okay, so you have to answer three times, three questions. So your friend gonna post one question, and you have to answer it three different questions. So far, you guys understand how it works for the forum?
Betul.
Okay. So after this, please read through this lecture note, and please, if you understand all, try to post at least one question, and then your friend gonna answer your question back. All right, and you yourself have to answer your friend question, three different questions. Okay, for example, you have answer friend A, you have to answer two more questions, B and C, for example. Okay, I think we shall start. Okay. Okay, now we move on to the deflector. Sorry, we move to the from deflector to propeller. So what do you understand about propeller? Can you comment there? What do you understand about propeller? What is the function of propel? What is the function of propeller? So by its name, propel. To propel what? High pressure. Okay, that is very simple, everyone. Like Amirul Hakim mentioned, to propel something by using the blade, by using the fan. So we have the fan. The function of fan is like a propeller to propel the fluid at the backward to the frontward. It's very simple. Okay. So now you can see here. Okay. Okay. So now we're going to play around with the energy equation and Bernoulli equation. That's why your fundamental on the Bernoulli and energy equation is very important. So here, this is propeller. Okay. From this statement, now the momentum equation apply to propeller. Previously, we discovered that momentum equation apply to deflector. Now we go to the second application, which is the propeller. The propeller require the momentum in order to extract the energy, right? So here, the momentum equation applied to propeller. Okay, the momentum equation in the control volume. Remember, we now in the phase of control volume analysis. We use the Renault transport theorem, RTT, from the system to control volume. So as you can see here, the line here represent the control volume. The outside here represent the control surface. And the previous week, I have explained to you what is the streamline. Alright, what is the streamline? What is the stream tube? So here, the line here, just imagine that we have the full of the streamline. The covering the streamline is the stream tube. It is like a tube. Inside the tube, we have so many of streamline. Alright, so let's draw the the flow. Okay. Okay, this is the propeller. Okay, this is a fan, yeah, simple fan. And then we have the stream tube, right? Okay, like this. Okay. I'm not good in drawing, but I hope you understand, yeah. So this one, this is the inlet. Okay. And this is the outlet. This is the fan. For example, this is the turbine. I consider it's a turbine. This is the turbine blade. Alright, this is the fan. So here you can see line here. Basically, alright, this is the ground. Okay, and this is and this is the turbine. Okay. Okay, so you can see this turbine. We have the blades. Alright, this is, we just take a look the cross section. Right, so this one, because of previously we learned about the streamline and stream tube, we form the stream tube like this. Basically, this is how the stream tube. Okay, we have so many of velocity profile here, velocity streamline. So you guys understand how what is the stream tube and the streamline? Okay, this is not the the tangible thing that you can feel. This is just the imaginary line we consider here. This we call as the stream tube. This is tube. Tube full of stream velocity. Velocity is streamline. This is the streamline. Okay. So far, you guys okay? Understand?
Yes, doctor.
Okay. So now let's go back to here. Alright? Okay. So here, let's make a separation here. Okay. So let's say this is point 1, and this is point number 2, and this is point number 3, and this is point number 4. Right? By apply the continuity equation, okay, now we assume that the cross-sectional area at point 3 and 4 is the same. Alright, this is only slightly different. Okay, so this is assumption. Cross-sectional area at point 3, when you look at from here, is actually almost the same size with the cross-sectional area of 4. Okay, so by using the continuity equation, Q1 equal to Q2, and we know that Q equal to AB equal to AB, 1 refer to 1, 1, 2 refer to 2 and 2. Okay, if the area at 1 is equal to area at 2, okay, let's say this is, let's use the point 3, it is easier for you to understand. Okay, this is point 3 and point 4. This is A3, this is B3, this is A4, this is B4. You know that A3 equal to A4. So A3 equal to A4, we can cancel out. Thus, we can say that V3 as well is equal to V4 by using the continuity equation. Okay, so far you guys understand? Managed to capture, yeah? Okay, and then assumption as well, the elevation here, the Z1 equal to Z2 and Z3 equal to Z4, the same elevation. So we can say that elevation Z1 equal to Z2 equal to Z3 equal to Z4. The same elevations. And we neglect the viscous effect. Right? We neglect the shear stress at the wall equal to 0. For example, the normal case, this is the pipe, this is the flow, and we have the velocity profile. Why the velocity profile comes from? Because of we have the shear wall. Now the shear wall is nothing. It is equal to 0. So it becomes, when the tau wall equal to 0, it will be like this. Uniform velocity profile. Okay. So in this case, it will be uniform because we are not any wall attached to this flow. This is only imaginary line. Okay. So from here, apply the Bernoulli equation. Okay, use different pen. Okay, apply Bernoulli equation at point, at point 1 and you can actually apply at point 1 and 3. Okay, at point 1 and 3. So you use the Bernoulli equation to apply at point 1 and 3. So what is the Bernoulli equation? Remember our Bernoulli equation. This is the basic formula. V squared over 2G plus P over gamma, okay, plus Z equal to, this is 1, this is 1, this is 1. Okay, sorry. If this is refer to 1, this is 1, this is 1, and this is 1. And refer to 3, this is V3 squared over 2G plus P3 over gamma plus Z3. Okay, remember that Z1 equal to Z3, we can cancel out. Okay, and then P1. Okay, now we need to rearrange the equation. Okay, you rearrange, rearrange the equation. Okay, all the right term will move to the left term. So V1 squared minus V3 squared over 2G, because this is positive, going to the left is minus. And then plus P1 minus P3 over gamma equal to 0. This is equation 1. Now apply Bernoulli equation at point, okay, at point 4 and 2. Again, apply Bernoulli equation at point, okay, apply Bernoulli equation at point 4 and 2. So V4 squared over 2G plus P4 over gamma plus Z4 equal to V2 squared over 2G plus P2 over gamma plus Z2. Remember that Z4 is the same with Z2, we can cancel out. And we rearrange the equation. Rearrange the equation. Okay. It will be like V4 squared. This one go to the left side. Minus V2 squared over 2G plus P4 minus P2 over gamma equal to 0. Let's say this is equation 2. And again, we need to apply Bernoulli equation at point 1 and 2. Okay, apply again Bernoulli equation at point 1 and 2. So again, so we apply. Okay, so here we actually not apply the Bernoulli equation. We add. Okay, later on I will explain to you why we need to apply at point 1 and 2. Okay, so here we add, okay, adding equation 1 and equation 2. Okay. Okay, apply equation 1 and 2. You can see here equation 1. P1. Remember our pressure at 1 is atmospheric pressure. So we can cancel out 0. And P2 is actually atmospheric pressure. We can cancel 0. So we can simplify equation 1 to equation 2, okay, leading to this equation. Finally, it will lead to, okay, it will lead to velocity 2 squared minus velocity 1 squared rho over 2 equal to P4 minus P3. Okay, this is actually simplification from equation 1 and equation 2. It will lead this equation. Okay. Alright, so far do you want to ask any question? The most important thing is your understanding. Okay, I would like to recap. First, we apply the Bernoulli equation at point 1 and 3 and 4 and 2. After that, we simplify the equation. We name it as equation 1 and equation 2. Adding those equations together, it will lead to this equation. Okay. So from here, apply the momentum equation. Okay, we can apply momentum equation in x direction. Okay, so summation of force in x component is equal to mass flow rate V 2x minus d1x. All right, so here, okay, you can see in this diagram, we have the force, all right, the fluid force going here, and of course, let's draw the force. We have the force, and then we have the force at point 3 and the force at point 4. The force at point 3 is going here. The force at point 4 going here. Remember previously I explained why the force at point 4 counter it, because this is the flow. Once we take the cross section, right, we have the counter force. This is, we have the force, and then we have force, and then we have force, and then we have another force. Do you still remember? I explained previously this one. Everyone? I still remember? If we have force here, we have the counter force. But we only focus this force going to the control volume. The same here. So this is actually the need. They try to neutralize. So we apply the momentum equation at the x component. Okay, this is x component. So we have capital F plus F3 minus F4. Okay. So we have the capital F plus F3 minus F4 equal to mass flow rate. Okay. And then V2x. So V2x, okay. So V2 minus V1. So V2x is equal to V2 minus V1. Okay. So remember that V2 is equal to V1 as what we derived earlier. Sorry, this is V3. Okay. So basically, this part, alright. So now we focus on point 3 and 4. Okay. We focus on point 3 and 4. So we apply at point 3 and 4 only because we focus at this control volume. So this is V4. Okay. This is V4 minus V3. And you can see that V3 is equal to V4 previously that we discovered. Okay. So V3 is equal to V4 based on our Bernoulli equation. This we can replace with V3. So V3 minus V3 is equal to 0. So that's why the summation of force here is force plus F equal to P times P3 times area 3. Okay. Minus P4 area 4 equal to 0. And we know that area 3 is equal to area 4. Okay. So we can factorize area. So from here, we move to the other side. F equal to P for A 4 minus P3 area 3. So A4 and A3 is the same. We can consider this one the surface area only. Okay. So here we can factorize. Okay, factorize area equal to P4 minus P3. This is the force. Okay, let's say this is this is equation 3, and this is equation 4. Okay, equation 3 and equation 4. Okay, adding together equation 3 and 4, which lead to this equation 3. You can see this equation 3 and adding together equation 4, this will lead to, finally it will lead to velocity at point 3 at the inlet of the turbine equal to half V2 plus V1, right? So this is actually the mathematical equation. You just need to solve by using factorization, expansion, substitution, and this is the final form, right? If you rasa rajin, if you hardworking, and then you can try to derive it. Okay, but this one I try to show you the concept only. Okay. So when the question asks, what is the velocity at point 3? Velocity at point 3 is actually equal to half the average velocity, which is velocity 1 plus velocity 2. You divide it by 2, you will get the velocity at point 3. That's it. So you only need to remember this one. V3 equal to half V2 plus V1. Very simple. Okay, so far so good. everyone? Okay. Okay, that's why this part I need you to focus more, because this have more on the derivation technique. Okay, now you understand, yeah? B3 is actually average of B1 plus B2. That's it, very simple. And the last part is the question definitely will ask you, what is the efficiency of the propeller? What is the power output from the propeller? So now you need to apply, okay, here. In order to get the power, okay, the power output from propeller, you need to use the energy equation. Okay, we need to use energy equation. So what is the energy equation? We apply the energy equation at point 1 and 2. Okay, so look at back the point 1 and 2 here. This is point 1 and point 2. Okay, remember our energy equation, which is heat of pump plus V1 squared over 2G. It is basically the same, almost the same with the Bernoulli equation, but the Bernoulli equation don't have the energy. Plus P1 over gamma plus Z1 equal to heat of turbine plus V2 squared over 2G plus P2 over gamma plus Z2 plus heat loss. Remember that we only focus on this cross-sectional area. There is no involve of the long pipe, so the loss is negligible. We can cancel out HL, heat loss, and we can cancel out Z2 and Z1. And one more thing, we can cancel P1 and P2. Remember that P1 and P2 are exposed to the atmospheric pressure, so it is cancelled out. So this one, we don't have any heat input of the pump heat, so cancel. So we only have the H of turbine, or we call as the heat of output. This refer to, okay, this refer to input, and all these refer to output. So the output here refer to power output from propeller. So this HT refer to the propeller. Okay, this is the output from propeller. So you can change the subscript T to P. Okay, if you have turbine, that's it. It is turbine. If you have propeller as the output, and you have to change to be the output. H of propeller. I say H pro. Okay. So based on the output of the H of propeller, H of propeller equal to, you rearrange this one move to the other side, then it will lead to a okay. Okay. So this one, basically this is not the power output from the propeller. This is power input. Power input. So this one previously is H of the turbine. Okay, H of the. Okay, so the only thing that we need to cancel out is H of turbine. Okay, so because we focus on the power input. Okay, so remember that the left side is the input and the right side is the output. So we only left on this term HP. Okay, so HP is a propeller input. Remember head of input from propeller. So I change the HP to H of pro equal to E equal to V1, this term going to the other side, it will lead to V2 squared minus V1 squared over 2G. Okay, this is the power input from propeller, V2 minus V2 squared minus V1 squared over 2G. Okay, so and again, we know that head of propeller is basically the work output and the work input over the mass flow rate and gravity. This is actually the previous equation. Head of propeller is equal to work, the power over m mass flow rate times gravity. Okay, so we need to replace H of propeller with this one. Okay, so work input over mg equal to V squared minus V1 squared over 2G. So gravity with gravity we can cancel out, right? And then it leads to the mass flow rate we can shift to other side. The work input of the fluid is equal to V squared, V2 squared minus V1 squared over 2 multiply with m flow rate. Okay, and this part actually we can expand to, remember that if we have this term, we can expand to a squared minus b squared is equal to a plus b, a minus b. Okay, so we can expand to v2 plus v1, v2 minus v1 over 2 multiply with m dot. Okay, this is how to derive the work input coming from the fluid. Okay, okay, this equation for the propeller input. So we need to find the propeller output. In order to get propeller output, we use the equation of work time force time displacement. Alright, so we divide all this with time. So divide with time, we lead to W dot equal to F B. This is velocity. Okay. Alright. So this is a V velocity inlet. V here is velocity inlet. Okay. Okay, this is the velocity inlet. Okay. And we know that the F here we can expand to by using the momentum equation, summation of force equal to M V2 minus V1. Okay, so we just replace this term. So M, okay, this is mass flow rate. Mass flow rate V2 minus V1. Actually, this momentum equation we apply at point 1 and 2. Previously, we applied at point 3 and 4, yeah? You can see here. This momentum equation apply at point 3 and 4. Okay, this momentum equation apply momentum. Okay, momentum apply at point 1 and 2. Okay, so you try to replace this one. This is V1. So here is output. Okay, I say as W output. This is W input. I put here I, WI and WO. So in order to get the theoretical efficiency, thus theoretical efficiency, this symbol efficiency, of course, efficiency is output over input. So work, the power output, okay, the power output divide with the power input. So what is the work power output? Here, the one that we have derived. The M, the rate, V2 minus V1 multiplied with V1 over the input is this one, the whole this. Okay, V1, sorry, V2 V2 plus V1, V2 minus V1 over 2 multiply with M dot. So we can cancel, now we can cancel mass flow rate, we can cancel with mass flow rate. V2 minus V1, we can cancel with V2 minus V1. Okay. And this lead to equation V1 over V2 plus V1 over 2. So you know that V2 and V2 plus V1 over 2 that we have discovered previously from this equation. Half V2 plus V1. Can we replace V3? Yes, we can replace the whole this with V3. So we can replace here, definitely you will get V1 over V3. So efficiency is V1 over V3. So far, do you guys understand on how to get the theoretical efficiency? Yeah. So you need, this is just a derivations, but the most important thing, you need to apply it. Okay. Okay, I think that's all for now. Okay. I think that's all for now. I hope that you enjoy listening and try to understand. If you're not really sure, please look at the video recording. Okay, Fikri Ruzalan, what's your question? Okay, I will send in the WhatsApp group. Okay, please switch on your webcam. Okay.